presenter, Mr. Emiliano Casati. Mr. Emiliano Casati graduated in Energy Engineering from Politechnico of Milano in 2008. Since then, he is involved in a double PhD program between Technical University of Delft in the group of Professor Colonna and Politechnico of Milano in the group of Professor Dossena. His research is focused in the ORC field, innovative concept and modeling methodologies, and is giving us a presentation titled Centrifugal Turbine for Mini ORC Power System.
Thanks, Chairman. Thanks, everybody. First of all, I would like to acknowledge my colleagues and friends from Politecnico di Milano, Matteo Pini and Professor Persico, and Salvo Vitale, who worked on this project as for his master thesis in our group from Politecnico as well, and of course under supervision of myself and Professor Colonna. This is a brief outline of my presentation. I will start with introduction, and then the rest is invisible, so I'll just go. First of all, a few words regarding ORC power systems. As you know, we have seen a lot of presentations talking about decentralized power. So this means the development of relatively small sized turbo machinery in this power range, 10 to 100 kilowatt electrical, for a number of applications. And of course, as you know, the turbine represents the most challenging components under a variety of points of view. So what about ORC turbines, briefly? The use of complex and heavy molecules as a working fluid allows, and this is the reason why it was initially started, all this field, allows for a simple turbine. Simple layouts, compact turbines, reliable, mainly because being the specific work, the enthalpy drop across the expansion typically much lower than for a simpler fluid. You have that the number of stages can be reduced, and the peripheral speed of the machine can be also reduced. Of course, we have drawbacks, and the drawbacks are mainly related, as we already know from this morning, from the variation in volumetric flow rate from, let's say, from the first stage to the last stage during the expansion path. And of course, being the speed of sound of these fluids typically low, we also have to cope with transonic or supersonic flows in the machine. Then another disadvantage for the designer is the unavailability of let's say, charts based on similarity rules, such as those that we have for axial machines. So there are several paths of research of interest, which are the development of non-conventional turbine architectures, as we have just seen from the previous presentation. And of course, the interest in having a reliable preliminary design tools like 1D tools for the sizing and the selection of the basic parameters for these kind of machines, being the variety of applications of working fluids on operating condition, basically infinite. This is a sketch of centrifugal turbine, but you have just seen in the last presentation, so I will just fly over this one. Main advantage is basically the message is that none of the disadvantages which hamper the diffusion of this kind of machines for steam, like the Ljungström development, hold in the case of organic Rankine cycle fluids. Main advantage is the increase of flow passage area in the direction of the flow. As you have already seen, this concept allows to conceive relatively easy and compact multi-stage assemblies. But of course there are fluid dynamics considerations which go on the drawback side of this concept. The application of this kind of machine for ORC power systems dates back to the 70s, basically in Milan, with the work of Professor Macchi, Professor Corrado Casci in his textbook. And the main advantage in ORC applications is that basically being the specific work comparatively low, basically you don't need a stator, you don't need a counter-rotating solution, as it was the case with the Ljungström steam turbines. So basically from here is the interest, and then this is the code we developed, which is called Z-Turbo. It's mainly developed at Milan, Politechnico, by Matteo Pini, which is also here. And it's basically code written in Fortran, which allows for the selection of the basic design parameters for ORC turbines, which basically provides the necessary boundary condition for a proper machine optimization, because as we also saw in previous presentations, CFD is a fundamental tool for the optimization of the machine, but of course you have to start from a geometry which is already kind of optimal. And so the only way to optimize these basic design parameters, like a number of stages, velocity triangles, meridional channel shape, and so on, is a simplified tool such as a 1D tool. What we developed is a code which allows for a, let's say, rigorous approach, meaning that we rely on a multivariable optimization. And the main features are the treatment of real gas, which is performed with a lookup table approach to enable for fast and accurate calculations. Is of course the tool is flexible under the point of view of turbine architectures, meaning axial flow machines, centrifugal outflow, centrifugal inflow, mixed flow, and so on, and also the loss models that are implemented are multiple. Okay, this is regarding the validation, but we validated the code based on a multi-stage turbogas test case, which is of course a little bit on the safe side, being the machine much more simpler than an ORC one, but this is what was available, and this is basically the result in terms of meridional channel, and in terms of efficiency, that basically we get a 2% discrepancy. But as I said, this is the only test case we found in the open literature. Then regarding the code, basically what Z-Turbo does is to solve, to determine a matrix of interest, in this case the efficiency, as a function of multiple geometrical and thermodynamic quantities, but doesn't solve the optimization problem. To achieve maximum flexibility, the code has been coupled with an external optimizer, which allows for the selection of different objective functions, variables, constraints, and so on. The search and search algorithm also. The code is the Dakota optimizer, which is developed at Sandia National Laboratories. You can find it on the web, you can use it, and it works fine. Then we applied this tool to the preliminary design of 10 electrical kilowatt centrifugal turbine machine. This was the application, and these are the boundary conditions for the design, which are basically the thermodynamic cycle taken from literature. And these are the conditions of such a cycle. As you can see, the expansion ratio is quite high. working fluid is siloxane before, and we select as a priori choice a centrifugal transonic turbine, meaning that the Mach numbers are limited to be below 1. So how did we proceed? Basically, this is the key point. We wanted to assess the scalability of design procedures which are openly available in the literature and as have been proposed, for instance, in this work by Combs for a potassium vapor centrifugal turbine, this work for an hydrogen centrifugal turbine, and this work we authored on the first application to ORC fluids. And all these works assume simplifying design procedures derived from the practice of axial turbines, basically, such as the repeating stage one. And basically, these are the key ingredient of such a simplified procedure, whereby, for instance, the radial chord of all the rows are kept constant. You have the angles of the blade angles, the geometric angles are kept constant. And basically, this is a typical meridional channel which results from such a procedure. And also, basically, the key points are that you can hand out with a convergent channel in the first stages and with a highly divergent channel with high flaring angles in the last stages. How did we proceed? Basically, we wanted to assess these for small machines, and basically what we found out was that this parameter here, which we call the centrifugal effect, and is plotted here as a function of the rho, basically that each even number is a rotor. And as you can see, and it is also quite intuitively, you can see that the let's say going towards larger diameters, you have that this ratio tends to 1, meaning that for larger machines, the last stages tend to become more axial. For small machines, you cannot allow such a trend. Why? First of all, because you cannot allow for a convergent channel, because the blade height is already limited by the small volumetric flow. And secondly, you cannot allow for such a large flare angles, because while in a 1D approach, this is not correctly weighted in terms of performance loss. We know that 3D effects, which are negatively impacting on the performance, are arising if we allow for such large flaring angles, as you see here. So basically, we found out that for micro machines, microcentrifugal machines, we have the first stages and the last stages have completely divergent needs. In particular, we have to reduce the blade chord in the first stages, having more, let's say, tangential geometrical angle, higher deflection in the first stages, while in the last stages we have to allow for larger chords and more radial flows. So how did we proceed? Basically, we had to free all the parameters. So basically, this novel procedure cannot rely on any simplified assumption. So you see, we select a 5-stage machine just in order to comply with the constraint of having a transonic flow. This is, of course, quite a heavy assumption. And so for each stage, we had that all the blade chord is free to change. So there are no more constraints like in the repeating stage procedure. The same can be said for the angles, and of course for the diameters and the velocity of the speed of revolution, which we cannot get from any similarity chart. So here you see several geometric parameters which we get from the literature and are mainly related with manufacturing constraint and so on. And also the flaring angle we constrain to a value which is much lower than you can find in the axial machine literature. We adopted as a search algorithm a single objective genetic algorithm, whereby the objective function is in our case the efficiency, assuming a certain degree of recovery of the kinetic energy at the outlet. So this is the main result. As you can see, the meridional channel is completely different from what you could get with the standard procedure, let's say. As I said, the radial chords tend to be much smaller in the first stages, and then they get bigger. And the efficiency we got is in excess of 80%, but again, this is just a fluidodynamic efficiency based on a simplified, we use the Craig-Cox method to predict losses, and also the Tropel method for supersonic, the supersonic case, which I will show later. And an important disclaimer is that we don't know how to account for Reynolds effect when scaling down this kind of turbines. So we also expect a penalty in efficiency for this effect. As you can see, also regarding the velocity triangles, the first stages tend to be much loaded than the last ones. Higher deflection, more tangential flows. So basically, the machine is changing completely from the first to the last stage. Then, just as a term of comparison, we removed the assumption of a transonic machine, reducing the number of stages for 3 stages, of course allowing for Mach numbers in excess of 1, so lower efficiencies. And you can see that the meridional channel shape is still, let's say, quite regular beneath development. Then we compared it with the published results regarding the radial inflow single stage turbine for the same application, of course. And you see that the efficiency we got for the 5-stage case is in excess of 80%, let's say, which is larger than what has been published. But most interesting is the speed of revolution, which is half, less than half, for the same output diameter. And then another term which we didn't account for are the disk friction losses, which we expect to be advantageous for centrifugal machines, since you have basically only one disk rotating at half the speed, and you have a cubic relation with diameter and a quadratic relation with speed. So we expect this to be on the side of our machine. So concluding, I presented you this tool we developed, and we already published the description in a work, let's say a previous edition of this conference. We developed a novel design strategy aimed at scaling down the centrifugal outlet architecture. And while this seems also from the industrial point of view to be an assessed technology for large machine, we kind of paved the way also for micro machines, and this technology seems to be interesting also in this range of size. That's it. Thanks.
Thank you very much. space for a couple of questions.
My question, are the profiles the same in your last solution? No. Different.
Sorry, close it. The profile, what do you mean?
Shape of the blades, completely different, yes?
With
In your last solution.
1 second. Sorry, I closed it. There we are. Here.
In solution 3-stage and 5-stage, completely different.
It's completely different.
Okay,
Yeah.
thank you very much.
Okay. No other question? Thank you very much, Mr.
Thanks.
Secretary.